Hey everyone, my name is Xuan, and today I'm here to present about PDDL.jl, a Julia library that provides an extensible interpreter and compiler interface for automated planning in robotics and AI. The name of this library derives from the planning domain definition language, a widely used standard for specifying symbolic models of the world that can be used by automated planning and robotics software to solve real-world problems. As an example, here's how PDDL can be used to specify the classic blocks world domain, with predicates such as block X is on block Y, and actions like stack and unstack. Having specified a domain like blocks world, as well as a problem description consisting of the initial state and goal, these PDDL descriptions are typically then fed into an automated planning system, which produces a plan or a sequence of actions that solves the problem. So that's PDDL itself. But what is PDDL.jl? Well, at a most practical level, it's a parser, interpreter, and compiler for PDDL written in Julia. You can use it to parse and load PDDL domains and problems, inspect the contents of PDDL state representations, determine which actions are available in a state, and execute them. These primitives can then be used to write planning algorithms, like heuristic-guided ASOR search, which in turn can be used to solve planning problems. At a higher level, though, PDDL.jl can be seen as a language framework for AI development, similar in intent to language frameworks for deep learning or probabilistic programming. Analogous to PyTorch for differentiable programming, or Pyro, Turing, and Gen for probabilistic programming, PDDL.jl provides an extensible programmable framework for automated planning that abstracts away from the low-level details of working with planning domains. And just like those other frameworks, it aspires to be user-friendly, composable, and high performance. It should be easy for users to write new planning algorithms and applications using PDDL.jl, and combine them with other systems and technologies, without sacrificing speed or other measures of performance. And just to illustrate this point, here's a taste of what PDDL.jl is capable of. First, it can be used to write symbolic planning algorithms that exceed widely used alternatives in performance and generality, achieving runtimes 10 to 50 times as fast as a Python alternative, and within an order of magnitude of a state-of-the-art planner written in C++. PDDL.jl can also be used to simulate PDDL domains as reinforcement learning environments. This allows existing RL algorithms implemented in a Julia ecosystem to be used with PDDL domains. In addition, PDDL.jl can be composed with probabilistic programming libraries such as Gen to perform Bayesian state estimation from partial observations. For example, here I'm showing how blocks world states, whose variables and relations are exposed by PDDL.jl, can be inferred under a partial observation model where only the topmost blocks are visible, or that model is specified in Gen. As more observations are received, the inference algorithm converges to the ground truth state. Taking this one step further, we can actually use planning algorithms built using PDDL.jl as agent models within Gen. This allows us to perform online goal inference via Bayesian inverse planning. And because planning in PDDL.jl is so rapid, inference over planning algorithms is too. These are just some of the AI applications enabled by PDDL.jl. Many more are possible. So what is it that makes PDDL.jl highly performant, but also so extensible and composable? To answer that question, it's helpful to compare PDDL.jl against standard planning algorithms, such as fast downward or fast forward. These systems are typically designed for rapid planning over a subset of planning problems, using a restricted family of planning algorithms, and often use bespoke compilers for PDDL domain descriptions in order to optimize performance. While this greatly benefits speed and efficiency, it comes at the cost of code reuse, extensibility, and integration within larger AI systems. This in turn limits the uptake of symbolic planning by researchers outside of the planning community, and inhibits the synthesis of symbolic, probabilistic, and neural approaches to AI that has been projected to play a key role in the next generation of autonomous systems. In contrast, here's the architecture of PDDL.jl and its surrounding ecosystem. Unlike standard planning systems, the core design target of PDDL.jl is a common interface for interacting with symbolic planning domains. This interface includes basic planning operations, such as executing actions, determining the set of applicable actions, or querying state variables, providing reusable building blocks for a wide range of algorithms and applications. In addition, PDDL.jl provides multiple implementations of this interface, allowing users to navigate the trade-off between extensibility, debuggability, and performance. The first of these is an easily extensible PDDL interpreter, which allows the semantics of PDDL to be augmented to include, for example, stochastic or continuous domains. The second is a compiler, which generates compiled implementations of the PDDL.jl interface that enable comparable runtime performance to state-of-the-art planning systems. And the third is an abstract interpreter, which allows for a wide variety of problem analysis tasks, including the construction of an abstraction-based planning heuristic for use within search. Because PDDL.jl's interface is sufficiently general, we can use it to write multiple applications, including many families of planning algorithms and heuristics, along with the other use cases we surveyed earlier. Furthermore, these algorithms can be used with any of PDDL.jl's implementations. For example, planning with a compiler can be used to speed up performance, while the abstract interpreter can be used to implement planning over an abstracted state space, which can in turn be used by planning heuristics. Finally, PDDL.jl is designed to be extended, either by leveraging its extension interfaces for custom functions and abstractions, or by implementing completely new semantics for its existing interface methods. This allows for the future development of extension libraries that support various descendants of PDDL, such as PDDL Stream for task and motion planning, or probabilistic PDDL for stochastic domains. Collectively, the goal is that these features will allow PDDL.jl to serve as a platform for contemporary AI algorithms and research programs that leverage the integration of symbolic planning with other technologies, including many of the applications I showed earlier. So that was a brief overview of PDDL.jl, its architecture, and its applications. If you'd like to learn more, I encourage you to check out the documentation online, or this master's thesis if you want more technical detail. There you'll find many other details, such as a description of the API that PDDL.jl exposes, how you can extend PDDL.jl to support new semantics, how PDDL.jl's support for abstract interpretation can be used to derive planning heuristics, and how you can use the PDDL.jl compiler to drastically speed up planning algorithms. With that, I'd like to thank my many collaborators and colleagues whose ideas and expertise in cognitive science, automated planning, and programming languages enabled me to embark on writing this library, as well as you in the audience for your time. Thank you for watching, and hope you enjoy the rest of JuliaCon.